This is just a little bit of the notes that I didn't get a chance to go over thoroughly with one of my classes or a couple of my classes, and I wanted to do so here on a video. Subsection 4 of the notes today was on power functions and end behavior. What a power function is it's something like this. It's just a monomial with a coefficient x and a power of x, or an exponent. So a power function of degree n is of the form f of x equals ax to the n, where a, our coefficient, is any real number, and n, our exponent, is any natural number. The behavior of a function for large values of x, either positive or negative, because we have x in the absolute value bars here, so that covers large positive and large negative. This is called end behavior. So if you're looking at a graph, as it runs away towards infinity on the x-axis and towards negative infinity, the way it behaves there is called end behavior. So it's not looking at what's happening right around, from negative 10 to 10 or something like that. It's looking at what happens way off on the ends. So we have a theorem here. It says, for large values of x, the graph of the polynomial function f of x equals ax to the n, blah, 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 blah. This is just a standard polynomial in standard form. So the graph of this polynomial will resemble the graph of the power function y equals an x to the n. An is just the coefficient of the largest degree term, the highest degree term in your polynomial. So the coefficient of the biggest exponent, and n is the biggest exponent. So if we had x cubed plus 2x plus 3, or let's look at this one here. We have 3x squared minus 2x plus 5. Our largest exponent here is 2x squared. The coefficient of that is 3x. So what I'm going to do for these three is write down the power function that approximates these polynomial functions at the end. So the ones that approximate the end behavior of these three. So I'm going to use the resembles or approximately equal to. For large x, this polynomial function is approximately equal to y equals 3x squared. Because squared is the highest degree term here, and 3 is the coefficient of that term. Alright, for the next one we're going to have to do a little bit more work. We have to figure out what the highest degree term would be. We can just figure out the degree of the polynomial, though. It works the same way. So I'm going to put resembles y equals, it's going to have an x here, so we need to figure out what the exponent of x is, and we need to figure out what the coefficient is going to be. First, let's do the exponent. We'll just figure out the degree of the polynomial. So we have x squared, and one more here makes it x cubed. So the degree of this polynomial is 3. The degree of the power function will also be 3. Now we need to figure out what the coefficient is. Well, negative 5 is the only constant being multiplied by both of these. So our coefficient will be negative 5 here. Negative 5x cubed. Alright, finally same thing down here. The polynomial function negative 3x times x minus 1 times x plus 2 squared will resemble at the ends, will resemble y equals, now we got to figure out the degree and the coefficient again. First let's do the coefficient this time. Negative 3 is the only constant that's being multiplied by all the x's. So the coefficient will be negative 3. And then the degree of this power function will be the same as the degree of this polynomial. So we just got to figure it out. We got 1x here. We're up to 2 with this term. 3, 4 with this term, because this one is squared. So the degree of this polynomial function is 4. The degree of the power function that approximated at the ends will also be 4. I could have just as easily put f of x equals 3x squared. This was the way the theorem wrote it. But we know f of x and y are equivalent for functions.